In this question, we have rate of reaction. We are given initial rate of the reaction in this table format, which is pretty common at this A-level standard. So the rate equation is rate constant multiplied by this concentration of ClO2 to the power of 1 despite the 2 here, as well as concentration F2 to the power of 1. What are we supposed to do here? So here, this is order 1 and order 1 with respect to each of these reactant. So what is meant by order of reaction? So order of reaction is the power to which you must raise the concentration. So it's a fixed definition. So it's the power to which the concentration of the particular reactant or particular reagent. So since they use reagent, I'll just use reagent, or you can say reactant, should be no problem whatsoever, is raised to. So you raise it to the power of that thing called order of reaction, and this is in the rate equation. As you could see in the rate equation above, you raise the power, the concentration of ClO2 to the power 1. That means it's first order with respect to ClO2. It is first order with respect to F2, such that the total number or the total order of reaction, there will be 1 plus 1, which is 2. That's called the molecularity of the reaction. Okay, so 2 molecules of that are involved in the slowest step of the reaction because, there's one of these and one of these in the rate determining step. So we need to find the rate constant, use the results of experiment 1. So since the rate equal to the rate constant, ClO2 and F2 like that, so I just make the rate constant the subject, and they do want us to have the units. That is for your 3 marks, well, provided you know how to do the units correctly. That is, so looking at experiment 1, the rate there, 2.20 times 10 to the minus 3. So make sure you know how to key that into your calculator, especially with the minus 3 there. And I have 0.010 to the power of 1, and then 0.060 to the power 1. I'm just going to play around with the units now. The mole per dn cube per second divided by mole per dn cube for the first concentration, and then the mole per dn cube for the second concentration. Having done that, you should hopefully see the mole per dn cube, one of it, cancel with mole per dn cube, or you could say cancel with that. So altogether, what am I left with? I'm left with second minus 1 mole dm minus 3. You cannot leave your answer like this. Unfortunately, you have to express it in the simplest form. So there's mole minus 1 dm to the power of plus 3, because 1 over that give you mole minus 1. 1 over dm minus 3 give you dm plus 3. Now that is second minus 1 there. So the unit will give me the 1 mark. The next thing really is to just press the calculator, 2.20 to the power 10 minus 3. So what you do is 2.20, and then you press EXP on your calculator. That means time 10 to, and then you press minus 3 divided by 0.010. Do not forget, divided by 0.060 as well. And I get my final answer is 3.667. But looking at the value that I have used, these are 2 significant figures, these are 2 significant figures, these are 3 significant figures. So, I could have put my answer as 2 or 3 significant figures. That would have been appropriate given the data in the questions. Should be no problem, 2 or 3 significant figure like that. So, I'm just going to round it up to 3 significant figure. And that's the unit there. Okay, if you give it to 2 significant figure, it will be 3.7. I've given it 3 just based on the 3 significant figure in this data that I've used there for experiment 1. 2 significant figure would have been okay based on these 2 data, which are the 2 significant figure, which I've used as well. Now the next thing is use the data in the table. Calculate the initial rate in the experiment 2. There are 2 ways to do this. You can use your rate constant from the previous question to calculate the rate in experiment 2, okay? Or what you could do is you could use the information here and you do rate 2 divided by rate 1. So I'm going to go the easy way first. So the easy way is, assuming my answer is perfectly correct, so my rate constant will be 3.67. And then my ClO2 in experiment 2, the concentration of ClO2 in experiment 2 is 0.025. So it's multiplied by 0.025 mole per dn cube. And then multiply that by 0.060 to the power of 1 there. And guess what? 3.67 times 0.025 times 0.060. What I get on my calculator is 5.505 times 10 to the minus 3. That is not very appropriate given that these initial rates are all to 1, 2, and 3. 1, 2, and 3 significant figures. So what is appropriate will be 5.51 times 10 to the minus 3. Well, I follow the unit of the rate of reaction in the table. There's mole per dm³ per second. This is the 3 significant figure. I said earlier there's another way, not necessarily another easy way. It's actually essentially is using the ratio method. So red 2 over red 1. So red 2 is what you want to find. The red 1 is 2.20 multiplied by 10 to the minus 3. And this is equal to K. And then this is red 2, right? So 0.025 and then 0.060. And then it's the same rate constant at the bottom, 0.010 and 0.060, like that. So guess what? You're going to get cancellation. So the top bit refers to red 2, the bottom bit refers to red 1. So K and K is the same there. 0.060 and 0.060 is the same there. So what you get is red 2 is equal to 2.20 times 10 to the minus 3 times 0.025 over 0.010. So they did say use information in the table. I don't think they will penalize you if you use, this method, because they just say use data. They don't say you cannot use any other information. You did use the data, but even if you press it on your calculator, 0.025 divided by 0.010 times 2.20 times 10 to the minus 3, I do get an exact answer, which is 5.5 times 10 to the minus 3. Again, the data in the table shows 3 significant figure. I think it would be appropriate to actually give these two 3 significant figure as well. So that will be 5.50 times 10 to the minus 3. It's got a unit of mole per dm³ per second. That's not too far from that because we have used a rounded up value of the rate constant. And this is skipping the rate constant step. And without really using the correct constant step, you can still get the same answer by this method. So you don't have to show both method. It's either of the two methods will have been okay there. Now use the data in the table to calculate the concentration of ClO2 in experiment 3. So we have rate equal to rate constant, ClO2, and then concentration F2. Now I want the concentration of ClO2. I make that the subject. So there's rate constant goes to the bottom, F2 concentration goes to the bottom. Once I rearrange my equations, I should be ready to just key in my value, 7.04 times 10 to the minus 3 for experiment 3. So there's 7.04 times 10 to the minus 3 divided by the rate constant. The rate constant was 3.67 from the previous bit of the question. And then this is what I want, and then this is my F2 concentration that is at the bottom there. So I'm just going to copy paste this formula now to my data below here. So remember that was your rate, that was your rate constant, and this is your F2 concentration. So 7.04 times 10 to the minus 3 divided by 3.67 divided by 0.040. So my calculator show me 0.04796. Looking back on the data on the concentration, these are all to 2 significant figure, 1 and 2, 1 and 2, 1 and 2, 1 and 2, 1 and 2. So it makes sense that I should probably give my concentration to 2 significant figure. There will be 1 and 2. So I look at that 9. So I get 0.048 mole per dm³ because I'm looking for concentration. And I give these to 2 significant figure based on the appropriate data from the question there. So 0.048 mole per dm³. The next question, what is meant by rate determining step? So rate determining step is the slowest step in the overall reaction. If it is the slowest step in the overall reaction, whatever reactants that are involved in the rate determining step, whatever reactants that are involved in the rate determining step will appear in the rate equation. Okay, whatever that appear in this rate determining step, the slowest step in overall reactions, will appear in the rate equation. And by the same principles of reversibility. If we work backward, whatever that appears in the red equations must be involved in the red determining step because they are involved in the slower step of the reaction. So we were told that this reaction between ClO2 and F2 has two steps. So red is equal to red constant, ClO2 and F2. You saw the overall reaction. What was the overall reaction just now? I thought I saw 2 ClO2. So 2 ClO2 plus F2 and then ClO2F. So overall reaction was 2 ClO2 plus F2 and then you get ClO2F like that. That doesn't make sense. Have I done something wrong? 2 ClO2F. Yeah, I mean the stoichiometry didn't quite work out just now. Anyway, so I have 2 ClO2F like that. So we can see in the slowest step only has one ClO2, only one ClO2 there, but here there's 2 ClO2. So in terms of the multi-step reactions, I could react my ClO2, one of it first, and then react with F2. So there's only one ClO2, there's only one F2 that can react to give me an intermediate, and this intermediate is the one that will react with another ClO2 to give me the final product. So here, I guess I get ClO2F because this is the product, ClO2F, but I don't get two of it because I only use one of these, so I only get one of these. As you can see, ClO2 is the same as ClO2, F2 and F, so that means I must have another fluorine atom here. This is like an intermediate. So what happened with this intermediate? Well, if I try to react another ClO2 with this intermediate, so this is like the intermediate does not appear in the red equations because how do you get one of this F? You get it from one and one of that. So together, if this is second step is a slower step, you would involve all together, not just one ClO2, because to get to that F there, you need one of that. So altogether, if step 2 is the slower step, it will be red equal to 2 of these, therefore it will be square and it will be 1 of the F2. But your red determining step is this, so that means this must be the slower step, and this is the fast step, because this is the red determining step. Slower step, only one of these and only one of that. First order with respect to each of these reacted in the red equation. That's the meaning there. So ClO2 plus F, I should get ClO2F. As you can see, this is an intermediate on the right, intermediate on the left. So the intermediate, when you add these two equations together, you're going to get 2 of that ClO2 plus 1 of that F2. And then this and this will cancel out as they appear on the both sides of the equation, and you get 2 ClO2F. That's the idea of, overall reactions, but not showing you individually what happened in reality. And one of the steps is actually the slower step. So state and explain which of the two steps is the slower step has to be the step 1, because in step 1, we have only one molecule of ClO2 reacting with one molecule of F2. Or you can say, so therefore, first order with respect to each. Yeah, okay. Or you could go the other way around, not step 2. So why not step 2? Not step 2, because if step 2 is red determining step, to get F as an intermediate, we already need 1 of ClO2 and 1 of F2, and then we would have red equal to K and then ClO2 square and F there. Okay, F2 there. Okay, because you don't have intermediate in the red equation, it can only be the reactant. So you need 2 of that ClO2, because to get these, you need 1 and 1 of that. So you will have ClO2 square and F2, and that is not your red equation as was told earlier. So this is not your red equation, this is your red equation. Okay, so I would say the blue one is probably a better answer. But I'm not saying that the pink one is not an answer. It could be. It could also explain why the first step must be the red determining step, because the second step cannot be the red determining step. Hope that makes sense there. All right, to the last bit of the questions. What is the effect of temperature change on the rate of a reaction? That is number 1. And then there is on the rate constant, there's number 2. There are 2 bits to this question. So describe the effect. So as temperature increases, that means a positive temperature change. So as temperature increases, particles get more kinetic energy. Okay, and your energy distribution, your Boltzmann distribution will shift to the right. You have more particles with energy greater than or equal to EA, your rate will increase. They are not asking for describe and explain, they're asking for describe for 1 mark. So as temperature increase, rate increases. As simple as that, right? And in your rate equation, you have rate equal to rate constant multiplied by blah, blah, blah. So as rate increases, rate constant will also increase. So therefore, as rate increases, so rate increases when temperature increases, and therefore rate constant also increases. Again, they are not asking for explanation, so there's no need for me to invoke the Boltzmann distribution explanation like in chemistry. For 1 mark, they just want the description of what happened there. And that's the end of that 9 mark question.